Uh, Hello, everybody. We are Team Aspire from IIITDM Kurnool, and this video presentation is for our phase 2 submission to the IEEE Signal Processing Cup. Uh, the phase 2 builds directly on our previously accepted proof of concept with targeted architectural improvements motivated by deployment and the perceptual performance. We begin revisiting the core problem. Visually, the camera can isolate the target through an optical zoom. However, the same cannot be reciprocated acoustically. The microphone array captures all sources in the scene with equal prominence. So audio-visual zooming actually aims to close this gap by enhancing only the speech corresponding to the visual speaker and the visual target. The official A.S.P.I.R.E Cup 2026 task formalizes this exact problem under severe constraints. The target speaker is not often dominant, interferers may be equally strong, and additive noise levels can be as high as 5 dBSNR. Scenes are reverberant, they involve multiple active speakers, and must be processed only using two closely spaced microphones in the aperture. Crucially, this entire system must also run on edge devices such as smartphones. So our phase 2 work is a continuation of a system developed by phase 1 team under the guidance of Dr. M. Kiran Reddy from IIITDM Kurnool. The same core team carried forward the design, analysis, and implementation into phase 2. To position our work, it is very useful to view it in a broader context of overall beamforming research. Unlike classical models, they provide strong theoretical guarantees, but degrade under model mismatch and low degrees of freedom. So naturally, learning-based methods seem to improve the robustness, but introduce challenges in the interpretability and comparably in the edge deployment. So modern systems increasingly combine these paradigms, which aligns directly in the intersection of our phase 1 and phase 2 designs. This slide captures the central design philosophy, and that remains unchanged from phase 1 to phase 2. So pure beamforming is highly sensitive to covariance estimation errors. Pure learning-based approaches are highly sensitive to spatial constraints and are difficult to deploy on the edge devices. So our solution therefore follows a hybrid of both of them. Uh, we tag them as a neural guided beamforming paradigm, where learning-based priors and beamforming enforces the physical constraints. We now revisit the Oracle reference used in our proof of concept. If a target dominant time frequency region is exactly known, then the noise spatial covariance matrix could be estimated optimally. This covariance matrix with optimal presence is called the true covariance matrix. This oracle defines an upper bound on the achievable separation and thus motivates the mass-based covariance estimation or the guiding process. This conceptual framework is identical to the phase 1 and is also introduced in great detail inside the proof of concept document. Now, in practice, the Oracle mask is unavailable since this requires to tap into the ground truth data. However, both in phase 1 and phase 2, we found a way to approximate this Oracle mask using a learned neural network followed by a beamforming backend. This Oracle mask is actually the component which will be guiding the beamforming backend. What changes in phase 2 is not the system topology, but the overall choice of the components. In phase 1, we used a deep FPU neural mask estimator followed by a switching MVDR beamformer. In phase 2, we replaced these with a speech-adapted EG unit and a continuous TFLC beamforming backend. Motivated by the improved perceptual stability and edge deployment, we chose to stick to the newer neural masks and the beamforming pipeline. However, the overall topology remains intact. So this is our overall proposed methodology and the end-to-end system pipeline. So it includes multiple steps, such as the input feature construction, the neural mask estimation, and followed by the beamforming backend. The detailed description of all these steps are given in the coming slides. Now, let's look at the implementation. The first step is feature construction. We simply don't feed the neural network into a raw audio file. Instead, we construct a specialized 5-channel 3D tensor to give the model a complete picture of the acoustic scene. So as you can see in the diagram, we stack 5 features, specifically the log magnitude spectrogram. This provides the basic spectral energy information, the sine and cosine of the inter-channel phase difference, or the IPD. We separate the phase difference into sine and cosine components, and this avoids the mathematical discontinuity of the raw phase angles, giving the network a stable representation of the spatial direction. The frequency map, and this tells us that the network in which the frequency bin it is looking at and provides spectral context. And lastly, the magnitude squared coherence, as this is the direct metric that helps the network distinguish between direct path signals and diffuse reverberation. By stacking these, we effectively fuse spatial, spectral, and coherence cues into a single input block. Now, once this feature tensor is constructed, it flows into our runtime inference engine. We utilize an ONNX, the Open Neural Network Exchange workflow, to build our training environment with the deployment environment. The process follows 4 strict steps: the STFT feature construction, and we convert the raw audio into the 5-channel tensor we just discussed. The neural inference tensor is then passed into the exported SAGE unit to predict the target mask, followed by the TFLC beamforming backend. This mask initializes the mathematical beamformer loops to compute the optimal weights. Finally, we apply the weights to use the inverse STFT to generate the clean audio output. We ensured that our inference output in MATLAB matches our training time behavior exactly from the Python pipeline. This consistency guarantees that the performance we measured in the lab is exactly what we delivered in the final submission. So now let's move into the core of our deep learning approach. To solve this problem, we first had to define exactly what the neural network sees and what it needs to do. For the input, we don't feed the raw audio waveforms directly, since they are too noisy and unstructured. We convert the audio into a time frequency log magnitude spectrogram, effectively turning the sound into an image, where the x-axis is time and y-axis is frequency. We will look into it in more detail in the further slides. The task then becomes a classification problem, where every single pixel or the time frequency bin of the image, the network must make a binary decision, and that is between is the specific part of the pixel target speech, or is it noise. So this formulation actually leads us to a critical insight. By treating the spectrogram as an image, this audio problem becomes structurally similar to a segmentation problem. So specifically in medical imaging, as we have time frequency input, we need to choose a binary mask that is as close as possible to the oracle mask. So because of this problem similarity of segmentation, we selected the unit architecture family. And the unit is a state-of-the-art model for such segmentation tasks, being famous for its encoder-decoder design. So the encoder compresses the image to capture the global context in encoding features, understanding things like speaker's gender or the sentence structure. Simultaneously, the decoder brings it back to its original size. Crucially, it uses the skip connections to transfer the fine-grained details from the input directly to the output. For this phase, our primary goal was to maximize the source separation quality. So we modified the unit by integrating residual blocks or ResNet blocks, and we started naming it the deep frequency preserving unit, or the res unit. In standard unit, as the data passes through multiple layers of convolutions and downsampling, critical feature information can get washed out or lost. By adding ResNet blocks, we introduce mathematical shortcuts essentially that allow the network to retain these features much more effectively. This ensures that the fine details of the audio signal survive the deep encoding process, and those aren't lost during the complex encoder-decoder operations. Furthermore, these blocks solve the vanishing gradient problem, allowing us to build a much deeper network than the standard unit, resulting in superior performance for difficult separation tasks. Here is the actual architecture of the phase 1 model. As you can see from the depth of the layers, it is massive and a dense network. Functionally, it worked. It provided high quality separation. However, practically, it was a failure for the edge deployment requirement. The specific design resulted in a model size of about 110 MBs for a smartphone that needs to record 4K audio, run an operating system, and process audio simultaneously. This simply is just too heavy. It saturated the memory bandwidth and failed our latency constraints. So we soon realized that brute force was not the answer. Facing this memory bottleneck, our immediate instinct was to compress the model. We used int8 post-training quantization, which reduces the precision of the network's weights from 32-bit floating point numbers to 8-bit integers. So on paper, it looked as if we shrank the model size from 110 MBs to 15.8 MBs, which looks deployable. However, the output performance was a total collapse. The STOI score plummeted from 0.74 to 0.56, and the PES score crashed from 2.12 to 1.52, 1.42. Since standard convolutional networks rely on high precision math to track the voice, when we take that precision away, the integrity falls apart. We couldn't just shrink the old model. We needed a fundamentally different architecture altogether. So this failure led us to our final phase to innovation, the speech adapted efficient group enhanced unit, or the SAGE unit. Instead of using heavy standard convolutions to process the audio, this architecture uses a mechanism called the group enhanced attention. Standard networks look at the audio in small local patches, but attention allows the model to capture the global context using very lightweight mathematical operations such as bilinear interpolation. So this resulted in a double victory. The efficiency of the model is just has increased because the model size is just 16 megabytes in full floating point precision, which is roughly 7 times smaller than our phase one model. And the performance also was skyrocketed because it understands context better. It actually surpassed the heavier model in terms of separation quality. So we solved the memory problem without sacrificing the audio quality. So in order to solve the memory bottleneck, we looked beyond traditional audio models and adopted the EG unit. And that is a highly efficient architecture originally designed for medical image segmentation, which performs like the transformers model, but with very low memory computation. However, raw audio spectrograms behave differently, slightly differently than medical images. So in order to bridge this gap, we engineered the speech adapted or the SAGE unit, and we modified the original architecture by injecting residual blocks into the encoder and decoder to stabilize the gradient flow and optimize the processing pipeline to better handle the spectral data. So this adapted architecture relies on two powerful mechanisms. One is the GHPA, which stands for the group hyperposition attention. So this is placed at the bottleneck, and this model captures long-range dependencies, such as sentence structure. And this does that using lightweight grouping operations, using very heavy attention layers. Second is the GAB, which stands for Global Aggregate Block. So this is integrated into the skip connections, and these blocks actively filter out the features passed from the encoder to the decoder. So this removes noise rather than just blindly concatenating like a standard unit does. So at this stage, once we have completed our neural discussion, we can now talk about the beamforming backend. So using the mask, which we computed using the noise dominant spatial covariance matrix by accumulating the time frequency regions where the target is absent. So this allows us to estimate the interference field reliably, even under very low SNR conditions. We then perform the eigenvalue analysis of this covariance matrix, and the ratio of the dominant eigenvalues give us an anisotropy measure, which tells us whether the interference field is spatially directional or diffuse. If the interference is directional, we apply an LCMV beamformer, where LCMV is well suited because it allows us to enforce a hard spatial null on the interferers while maintaining a distortionless response. So unlike MVDR, LCMV is designed to null out the stronger interferer rather than try to null all the interferers equally. And given a situation where we are having a constrained amount of microphones and degree of freedom, such an approach was suitable for a better separation and a better SIR. On the other hand, if the interference field is diffuse, this hard nulling becomes unstable and is problematic, especially with only two microphones. In which case, we had to switch into a diagonally loaded MVDR beamformer, which provides better numerical stability and a smoother separation. So this was our strategy, our beamforming backend for our phase one system, to adaptively select the appropriate classical beamformer based on the spatial structure of the noise, which is estimated from the from the neural network. So in phase two, instead of making a hard decision that as we made in phase one, we move on to a continuous formulation using the TFLC beamformer. TFLC stands for time frequency pairwise linear combination of beamformers. So the idea here is simple yet powerful. Rather than choosing between LCMV and robust MVDR, we compute a weighted combination of the candidate beamformers in every time frequency bin. These candidate beamformers are still classical designs and primarily the MVDR type, and each optimized for different interference characteristics. We then solve a constraint optimization problem to find the optimal weights that minimize the output power while enforcing a sum to one constraint. This guarantees that the target signal remains distortionless. Conceptually, this replaces the discrete switching logic of phase one with a smooth interpolation between beamformers. As a result, the system adapts more gracefully to mixed or rapidly changing interference conditions. Importantly, this approach preserves the interpretability and physical grounding of the classical beamformers while significantly improving robustness and perceptual quality, especially under the very severe 5 dB SNR and low aperture constraints of the SP-Cup task.
Hinder claimed that the man ran down the east side of Tavern and passed within 10 feet of him before crossing to the other side.
To the land of the Lille. There's no sorrow there, Jean. There's no call or care, Jean. The day to the land of the Lille. There's no sorrow there, Jean. There's no call or care, Jean. The day.
So, to rigorously validate our solution, we conducted a comprehensive benchmarking study against both internal prototypes and external state-of-the-art models using the standard asteroid toolkit used by many researchers. Crucially, every single model on this list was evaluated on the exact same dataset of 500 independent test cases, and this ensured that the numbers you see here are a direct comparison of performance under identical acoustic conditions. So let's walk through these results row by row to understand the true trade-offs. First of all, the theoretical upper bound, the true covariance matrix, and the oracle at the top, it achieves a separation of 31.38 decibels with a PESC score of 2.91. This represents the physical limit of what is mathematically possible with this specific microphone aperture geometry. Now let us look at the internal ablations and how the models and the backend beamforming have been developed. So our very first model, the comparisons with deep FPU and TFLC, this was the uncompressed phase one model, and it achieved excellent separation of about 23.33 decibels with a PESC score of 2.12. However, the model size is 110 MBs, which delivers quality but is just simply too massive for edge deployment. The quantized version, as we discussed, the model size went down to 15 megabytes, but however, the separation dropped from 22 decibels to about 13 decibels, and critically, the STOI score, which measures the intelligibility, fell to 0.56. This confirmed that single compression destroys the signal. So the most interesting comparison out of all is the deep FPU plus SMVB comparison. And you will notice that it has massive SIR of about 29.383 decibels. However, which is higher than our proposal, which is likely caused due to the SMVB. However, the PESC score and the STOI score are significantly lower than the proposed method. This is because the SMVB backend uses a hard switching logic, and it aggressively cuts sound to boost the SIR number, but it leaves behind robotic artifacts and musical noise that can hurt human listening quality. So naturally, we wanted to find a trade-off between the separation which we are achieving and the audio quality which we are achieving. So we then compared against the external benchmarks. So complex spectral models such as TCCRN and DCE-UNET, surprisingly, the popular models failed completely in our test environment, achieving SIRs below 6 dB and OSNR scores under 5 dB. They proved too fragile for our specific reverberation and aperture geometry of this challenge. ComputationNet, however, was our closest competitor, achieving a respectable SIR of 21.35 decibels and PESC score of 1.8. However, at 25 megabytes, it is nearly 60% heavier than our solution, which makes it less efficient for battery-powered devices. DPPRN, while extremely lightweight at 10.4, simply could not match the separation power. Its OSNR was 7.1 decibels compared to our 9.4, meaning it was 100 times lesser in magnitude than the proposed solution. Finally, our proposed method, Sage Unit and TFLC, it hits the perfect spot across all metrics. It achieves an SIR of about 22 and OSNR of 9.1 decibels, nearly matching the massive 110 MB models. In terms of quality, it delivers the highest PESC of all, of about 1.95, significantly outperforming the SMB backend and external baselines, ensuring natural sounding speech. And in terms of efficiency, it does all of this with of a footprint of just 16.4 megabytes. And we achieve the performance of the heavyweights essentially with the efficiency of the lightweights.
Going through the code demonstration and code explanation part of the presentation. So as you can see, we have structured our whole code base in the directory as mentioned in the document. In the as we have the folder for tasks and anechoic, task to reverberant with the respective audio files with the mentioned audio naming conventions and the .m task files to process the audios. Now we have separated our code in a modular way. We have created separated .m files for as helping functions to run the process task one, as you can see in the SRC and utils. And we'll go through them detail one by one what they are. So let's start with process task one. So this is process task one. This is basically for anechoic task. Here you can see we are loading the .mat file through data through the .mat file, and we are calling the functions of feature extraction inference function for processing the whole file. What these functions do, we'll look into it. So let's go to the process task two. This is same. It is the same as process task one. It takes the model as the model path and model input and calls the function of feature extraction and inference function to process the audio and give us the processed audio as final output. Now let's go through the individually what these functions do. So first see the feature extraction. So feature extraction is basically we are taking the audio file as input, the WAV audio, mixture audio files, and we are extracting the features that will be given to our neural model. So the features are something like interface difference, sine and cos of interface difference, the log magnitude values, and the MSC mean square covariance value. So these are get stacked onto each other, and we get a five length of vector feature vectors. That is, you can see. So our final input for the model becomes frequency, cross time, cross channels, where the channels is the five features. So you can go through this code as this is the feature extraction. Now we'll go through the inference function. This is the main function that runs the main pipeline. So what does it first calls it takes the raw audio as input and also the neural input that we just extracted from the feature extraction function. What it does, it setups the uh, model runtime using the ONNX. So what we have done, we have used the ONNX runtime for inferencing through the model because .pth is not compatible with MATLAB. So we have set up the whole ONNX files runtime, and it is taking the model is taking the neural input as its input, the frequency cross time cross channels as input, the image, and it is giving us the mask, the raw mask. Now, after applying some padding and some other post processing to the mask, we are giving the mask to our beamformer, the TFLC beamformer. As you can see, we are calling its function. We'll see how it is being implemented in this .m file. And after once we get our final raw output as raw output, we apply inverse STFT to get our audio from the spectrogram. Now, one thing I should mention that we have done a custom implementation of the inverse STFT as the native MATLAB implementation was little mismatched with what we have done in the Python implementation, and the results were mismatched. So we did a custom uh, implementation of inverse STFT to make sure that the padding in there should be the central padding. That was with the case of the SciPy and not in the native MATLAB. Now we go through the TFLC beamformer code. So TFLC beamformer is basically is core logic is about iterative optimization loop. So what it does, the normal beamformers go with the one-shot calculation. But here we refine the beamformers over some iterations. Here we have chosen that those iterations as 20 and the number of beamformers is 2. So we calculate the dynamic mixing weights for every frequency bin that are strictly constrained to sum to 1. So this is our kind of a distortionless guarantee. It ensures that no matter how aggressively we attack the noise, the target speech remains perfectly protected. So you can see this is a code. We go through the iterations, all the iterative optimization for 20 iterations and get the best weights. Now let's see the reconstruct audio function. So this is basically the code of, as I told you, that we have done a custom inverse STFT implementation. So this is code for that. You can go through it. So now after the code explanation, let's go through the how to infer and how to run the whole pipeline. So for that, let's come to the VS Code. This is the same directory as you can see. So for running this whole file, we first need to initialize our mat file. We have the audios files as the same with name conventions and the process task one in the folder. But first we'll run the initialize mat.py. What it does, it will just take it will it will take our file and and write it into the mat file with the parameters and the configurations as well. So yeah, as you can see, all these details have been written in the MATLAB file, our audios and the other parameter data. Now, what we'll do, we will go through our MATLAB, we'll go to the MATLAB again, and now we'll again run our process task 1 and process task 2. So we are going to run the process task 1 as we have the .mat file here with us. It's running as you can see. So as you can see, the process task 1 has been completed and we have got our process signal.web in the same folder. Now we do the same thing for our process task 2. So we'll run it again. Here we go. So we can see it is running. So as the task 2 has been also been completed, as you can see. Now we'll see that there are we have the process signal.web in both the task 1 and task 2, and now we will see the metrics. So we have given a metrics.py that will basically take these audios, the inference and interference target and the processed, and calculate the standard metrics that were given in the document, and also append them into the .mat file. So the metrics have been calculated and they have been also appended. So in the same manner, if we want to test some other test case, we will just need to place the audios in the folders with the naming conventions and run the Python and MATLAB files in the same way. So this was the code demonstration. Thank you.
So with that, we come to the end of our presentation. We covered all details regarding our approach, starting from the motivation of the solution framework to the individual elements for the same. And we concluded it by looking at both the qualitative and quantitative results and the implementation details about the pipeline. Further, the paper discusses the mathematical and model architectures in greater depth. Thank you for your time.